Alright, so, next question.
We can move on to probability.
How many anagrams of bananagram are there?
That one's a good one.
So I have to first figure out how the heck you spell bananagram.
It's a good game.
Bananagram? Like this?
NPR.
Okay, so, yeah, this is kind of a permutation question.
Circular permutation.
No.
No, it's a.
It's a
NPR.
permutation with,
Order matters. Similar items.
yeah, so, hang on. So, yes, order absolutely matters. Why does order matter?
Because
Because nobody wants to play called my hamburger.
No. Okay, maybe, but mostly because you're rearranging the letters in a word, right? So the order is literally the thing that matters. Otherwise, it's just a sack with numbers in it, right? Or letters in it. You guys kind of see that? So I'm really talking about the order. So I know I'm going to do a kind of a permutation thing. Okay, so then I have to think to myself, how many things do I have to arrange? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10?
6. Well,
10?
6 once you combine all the like things.
So, wait. I have 10 factorial. That's
All the A's and the N's.
That's 10 things permuted 10 ways, right? There's 10 slots to re-permute these. But then you're right, some of them are the same, right? So there's like A's. You can't tell the A's apart. So how many A's are there?
4.
4. So you need to divide by 4 factorial, because rearranging the A's doesn't matter.
Doesn't matter.
You guys see that? So I'm dividing out by the number of rearrangements of the A's there are. Are those the only similar items?
No, there's 2 N's.
Oh, there's 2 N's. So I need to also divide by...
And you pretty much just, is it pretty much 10 times 9 times 8 times 6 times 5?
Sure.
Because you just cancel out the...
Yeah, so you could cross some stuff out, right? And think to yourself, okay, so right now, I have 10 times 9 times 8 times 7 times 6 times 5 times... Oops, that stuff got canceled.
Yeah.
Okay, and then... But I'm not quite done, right? Because there's still 2 N's.
Yeah.
So this thing here represents... Right, every anagram that's represented in here has 2 N's in it that I could switch, right?
Mm-hmm.
But switching those 2 N's isn't going to do anything to... It's going to be the same anagram, right? So I need to divide this by...
9. 3.
No. 2. Because everything's double counted because you've got this pair of N's that you could switch. So really I needed an over 2 factorial here. And 2 factorial is just 2.
I said 6 factorial.
Oh, 4 factorial times 2 factorial isn't 6 factorial.
I'm trying to figure out how. I know there's
So,
no logic behind it.
4 factorial times 2 factorial is 4 times 3 times 2 times 1 times 2 times 1. Right? And 6 factorial would be 6 times 5 times 4 times 3 times 2 times 1.
Okay.
Right, so you're like, okay, so this stuff agrees, right? But that's 30 and that's 2. Kind of overcounted a little bit.
That makes sense. I don't know why.
And it's also not 8 factorial, right? That's way bigger. It really is just 2 times 4 factorial, or 4 factorial
So what
times
would you
2.
do there? Raise the factorial basically?
So all I'm saying is go like this.
That's the answer.
That's the answer. And if you want a number, you can take this one and divide by 2, right? You guys with me on that?
Yeah.
I always thought you had to find a number.
I
I don't
mean,
care.
when you do that, you get a number.
Yeah, I mean this is a thing you could get a number out of, right? You can multiply it with your calculator. But the numbers are really big generally.
Yeah, I know, that's why they discriminate.
And also, oftentimes the next thing you do after you calculate like the number of possible ways there are to do this, is you're really looking for a probability usually. So this is just the thing that goes on the bottom of your probability, and then there's something on the top, and you can do a little cancellation before you calculate.
Okay.
Does that kind of make sense?
Alright, we can do probability now.
Okay.
I understand.